I had a difficult time trying to come up with a title for my talk. A title that's maybe more descriptive of some of the things we'll talk about is a probabilistic theory of deep learning. But what I'd like to start with is talking a little bit about water and cycles. And signal processing that I'm talking about today was born in the era of physics. But we are now in a model-based world, and now we're awash in a cycle or a tsunami of data. And in order to think about what's going to happen in the future when the next wave hits us, I think it's instructive to look back into the past. I don't know, a couple 3,000 years. So let's go back and think of Babylon. Okay, any Babylonians in the room? I think there was a contingent, but they couldn't get a visa, I think. So the Babylonians, so they were obsessed with data, right? They're obsessed with data and calculating. They were unbelievable at calculating, polynomial curve fitting. They could make predictions of celestial occurrences like eclipses extraordinarily accurately. They were so obsessed with data that they actually trained students to learn about how to process data by doing what? Just working large numbers of problems until the students got the basic idea. Does that sound like anything familiar? Yeah, I think it does. Because of this, even though they knew all of the key theorems, like, for example, Pythagoras' theorem and other results, they were completely incapable of scaffolding these together and really doing anything other than just polynomial prediction. Okay, so that's the Babylon. So this next slide's for Alex. So let's talk about the Greeks, right? The Greeks were very different. They were obsessed with models, right? And they were actually not so great at calculating. Here's one of their ridiculous models, right? That the Earth, right? The Earth is a big riding on the back of a tortoise, and the stars are basically there's a gigantic colander, right, with holes punched in it, rotating around. This is true. This is all. Alex believes this stuff, okay? And stars. You see stars, right, as the holes punched in this colander. So the Babylonians and the Greeks, and of course we need both of these approaches, right? The approaches rooted in the real world and also in our imagination to solve really hard problems. So I'm not talking about easy problems, right? All these kind of problems that are solved. We're interested in this meeting at solving really hard problems, right? Wicked hard problems. In particular, problems related to, my group's very interested in problems related to machine perception. Right? Problems like object recognition, speech recognition, robotic navigation. And what's difficult in these sort of wicked hard problems is the large amounts of nuisance variation that factor into these kinds of inference problems, right? There are multiple different nuisance variations. Think in this case the position of Dave's head within the image frame, the rotation of his head, occlusion, lighting, Dave with glasses, or different glasses, Dave with hat, etc. Right? And of course, in really difficult, many kind of problems that we're dealing with on a day-to-day basis, we might not even know the nuisances explicitly. Right? So we just have to cope with them in some kind of way. And this has been talked about already. What happens with nuisance variation is it really complicates the geometry, right, of the problem. In this case, if we're trying to build a classifier to tell Dave from Stefan, right, and we think of each picture of Dave and Stefan as living in a high-dimensional pixel space, then as we think of perturbing Stefan and Dave with these nuisance transformations, then the geometry or the manifolds that these images live on becomes very tortured and very intertwined. And of course, the grand challenge of machine perception is to find methods to somehow straighten out, right, or make simpler this geometrical structure. So hopefully the problem of separating, for example, Dave from Stefan becomes easier, right? So what we'd like to do is somehow disentangle, right, these nuisance variations. And in the past, of course, there's been a whole host of decades of work in feature representations that has been more or less successful. But we're here today to talk a little bit about deep learning. Just show of hands, how many people here are feeling pretty confident with the fundamental blocks of a convolutional neural net? We've had many talks on this. Big show of hands. It's 5 o'clock, right? I'll go faster if everybody raises their hand. So the first thing you do is you convolve, right? You have a template or a filter, and you convolve it, right? Slide it around in the image, taking inner products, basically looking for matches. So that's step one. Step two is then you sparsify with some sort of thresholding. This is neural net, so you can't call it, or computer science, you can't call it thresholding. You have to give it a fancy name. So we call it ReLU, right? Anybody know ReLU? I think he's president of the IEEE Signal Processing Society. Okay. We put ourselves through a threshold, so we throw away small values, keep large values, and then we downsample, right? There are multiple ways to downsample. One example being max pooling, that we take a high resolution image or feature map and we create a lower resolution image or feature map, not by the usual kind of wavelet-like subsampling where we average over blocks and then downsampling. We can also do things like max pooling, which is to take, for example, this yellow lower right subblock of this image and then take the maximum value, right, from that particular block. Okay, so we then do this convolution thresholding or nonlinearity pooling many times. Maybe 5, maybe 10, maybe 100, right? And it looks like this. We start with an image, output of the convolution. Since the filter in the upper left is like an edge detector, we detect, roughly speaking, vertical edges. We threshold, throw away the negative values, downsample, and repeat in a kind of a spin cycle. We can use this, we can train, right, this system to do inference by learning the weights of these filters. And typically what we do is we do this convolution thresholding, downsampling multiple times, take the output of that and just feed it into an old school neural net, right? Okay, and then we learn the entries of these filters by some kind of gradient descent type technique, typically with multiple graduate student thesis worth of tricks, right, in order to speed up this gradient descent. Very important, right, as has been mentioned, training is incredibly computationally intense. Okay, things really moved forward starting in 2012 with the advent of big data sets, big computing, and some amount of fancier architectures, in particular the convolutional neural net idea. Neural nets are everywhere now. They're they're going to take your lawyer's job. They're going to drive your car. They're going to cure cancer. They're going to actually solve climate change. So it's no wonder that these sort of black box, right, learning techniques are really taking off, right, and in the world. Okay, so. So now we can ask some questions, right? So what would the Greeks ask about this very Babylonian technique of deep learning, right? So here's some questions that have bothered us over the last few years. One is, why does deep learning work so well? Do we really know? We're not really sure. Can we derive deep learning from first principles rather than just positing an architecture? Why and how does deep learning fail, right, when it doesn't work? And can we improve these methods in some kind of principled manner rather than, again, through some kind of gradient or a graduate student descent? There's been a large amount of work emerging, or fairly large literature emerging over the last few years in this. And so what I'd like to talk about is our particular sort of take on developing some answers to these questions. Okay? So what we're going to do, just in a nutshell, is I'm going to talk about a probabilistic graphical model that comes out of statistical signal processing, something very standard. And what we're going to do is we're going to build that model, and then we're going to see, this is a spoiler alert, we can see that under certain conditions, the inference under this graphical model, the inference algorithm, is precisely the calculations that go on in a deep net, right? Therefore, right, we can hopefully, we'll talk, can answer these questions. Okay, does this make sense to everybody, or program? Okay. Okay. So, so we're going to develop a model. We're going to look at optimal inference under that model, and then we're going to look at how that optimal inference corresponds to the calculations in a deep net. Let's keep everything concrete by just thinking about object classification type problems, right? Is an image a picture of a cat, a boat, or let's say Stefan? Okay. So very simple graphical model, about the simplest possible graphical model. C, show of hands, graphical models. How many people? Okay, very useful thing. So let's C represent the class, cat, Stefan, right? G, the nuisance variables, right? Nuisance variables, and I is the image. So the graphical model is just a simple model for the probability of the image given C and G. This is a generative model because given C and G, we can generate the image, right, by flowing down this graph, okay? I is observed, C and G are not, right? They're latent variables. Okay, so how does this work? Let's say we want, and I'm going to talk at a very, very high level, right? All the details are in a NIPS paper from last year that you can refer to. So let's say we want a picture, generate a picture with our model of a happy cat facing left. So we set C to cat, we set G to happy and facing left, and then we are going to set up our image I as a rendering function, R of C and G, right, plus some noise. So we're just going to add noise to this rendered image. And for now, just think of when we want to render an image, we have a C and a G, and we run over to the telephone and we call Pixar, and we say, generate us a happy cat facing left. Okay, just for now. Okay, later we're going to relax this later from a purely generative model to a discriminative model. Is this clear to everybody? Okay, so this is at a single scale, right, or at a single level. Next, we want to take this model and take it to multi-scale so that we can think of generating images in a multi-scale or hierarchical way, where we can think of different nuisances acting at different scales, for example, and we can think of modeling the image at different layers of abstraction. And so basically, we take that very simple model that I showed, and what we do is we build it up hierarchically. So if you look at the very bottom 3 nodes there, that looks like just like the model I talked about. Now Z is a feature map. It plays the role of like the class. The G's are nuisances that play a role at different levels of abstraction. And C now comes in at the top, right? So C comes in at the top, says there's a cat in the image with a number of nuisance parameters that tell us what the cat looks like, for example. We flow down through the model and generate our picture of a cat. The way that we flow down through this model is with a very simple set of affine transformations. So again, let's just focus in on this red bubble here, right? Given a feature map at scale ZL, and the nuisance variables at that scale G, are GL, we want to generate ZL minus 1. And we do that very simply just by vectorizing ZL. Here's vectorized ZL, operating on it with a matrix, a linear transformation, adding on a bias to make an affine transformation to create the feature map at the next finer scale, which then, if it's an image processing problem, we can reshape back into an image. Okay? We call this affine transformation lambda, and the important thing is the nuisance variables are what control the entries of this affine transformation. So if you think now of cascading from the top scale down to the bottom scale, we are basically talking about an image synthesis machine that simply just constructs images or generates images just by a product of affine transformations. Right? So we're a product of these affine transformations. So so it's a graphical model. If you're not familiar with graphical models, this might seem, well, if you are familiar with graphical models, there's very standard things that you can now you can do. So in particular, there are message passing algorithms that will perform efficient and, in some cases, optimal inference, right, for problems with this particular graphical model setup. In particular, our model is very close to a tree structure. And for a tree structure, you actually have optimal inference using message passing for a variety of different inference tasks, in particular classification. So you can perform various algorithms like max sum product. People might know terms like forward-backward type algorithms, Viterbi type algorithms. These all perform optimal message passing in order to make inferences. We can think of inference as two different possible passes. One is a bottom-up pass. Given an image, infer the class label CL. That's like a inference. And then we can think of a top-down pass. Given cat, the class cat, and a particular picture of a cat, infer the latent variables G. Okay? We can also learn. Again, if you use graphical models, there's an algorithm called the EM algorithm. Show of hands. It is just the standard way to learn in a graphical model. And there's decades of literature, right, around developing nicely tuned methods for solving the learning problem, meaning learn the entries of the affine transformations in this case, given a bunch of training data. For example, in a supervised case, say labels and images. Okay, so learning. So summary, right? Summary so far. We talked about this thing. I'm going to call it the deep rendering model, or the DRM. Tan wants me to call it the DRMM, but we'll keep it simple. It's generative, so it synthesizes images in a top-down way, right? Starting from a class to create a picture. But we can do optimal inference, for example, classification, in a bottom-up way, right? In a bottom-up way to solve via very efficient message passing, in this case, max sum message passing. And given some training data, we can learn this model via the EM algorithm. This is totally standard, right? This is, again, like 1980s, 90s stuff, and it's really bred these kind of algorithms are deployed in just all over the place. Okay, so why is this interesting? Well, this is interesting because you can prove, okay, that this bottom-up inference pass, right, in this graphical model that I just described, this deep rendering model. I've tipped it on the side, so it's a left to right pass. If you actually write out the message passing calculations, they're precisely the calculations that go on in a convolutional neural net. Precisely, right? Convolution, thresholding, max pooling, right? As we'll talk about in a second. Okay, which means that maybe we can gain some insights into deep nets by exploiting the decades of work that has been gone on in understanding the behavior of these tree-structured or close to tree-structured graphical models. You can have a look at the NIPS paper for the details, but the key takeaway, right, is that convnets, this Babylonian approach, can be endowed with a very rigorous probabilistic Greek structure. Okay? Clear to everybody? High level. Okay, so now let's talk about the proof. And for the proof, people know there was just a government shutdown. And coming out of the government shutdown, there was just a directive. I don't know anybody who has an NSF report due anytime soon, but now when you submit through Fastlane, your project summary now has to be fit in the length of a tweet. It has to be 140 characters. Okay, a new directive from the government. And so we're actually going to do a proof by tweet, okay, of this theorem that this deep rendering model, the inference calculations correspond to the calculations that go on in convnets. Okay, so it's going to be very, it's going to be quick. What we're basically going to do is we're going to make some assumptions about the nuisance variation, right? And those assumptions about the nuisance variation are then naturally going to just induce a structure on the message passing optimal inference calculation. And the first assumption is that we're interested in classifying a target, but there's a translational nuisance, right? We don't know where the head of the person is right, in this particular image. So we have a translational nuisance. So let's assume that the nuisance is translation, and let's assume there's noise added to our image, and assume it's white Gaussian. It doesn't have to be Gaussian, but exponential family. Okay, this is a very, now this is a very standard classification problem that occurs in radar, sonar, all kinds of other problems, right? So we're trying to find a target, submersion white Gaussian noise, where we don't know the translation of the target. Well, we know the optimal classifier in this case. It uses Covifi, right? Also known as convolution to you people not in the know, with a match filter, right? Match filtering classifier, right? And so this immediately pops out convolutional layer, right, as the first calculation that goes on in this message passing as we move up through the tree. Okay, next, we have to patch up a problem with our model. The problem with our model is it's a little bit oversimplistic in that if we want to generate an image with this generative model that both has a picture of Dave and a picture of a hand, then it's entirely possible that the hand and the face will be co-located. But what our model will actually generate is not a picture of a hand in front of a face, but actually a cross-faded sum of a face and a hand, which is not what goes on in real imagery. This might be realistic in acoustic signals, but it's absolutely not realistic for images, for example. So what we have to do is basically ensure that that doesn't happen. One way to make that not happen is when we're thinking about generating images or patches of images from this particular model, we can put a sparsity prior on this generation process. Okay, so now if we think of introducing the sparsity prior, and we think of optimizing the most likely configuration of those sparsity values, right, in this tree generative model, it turns out that the optimal processing to actually do is precisely a thresholding, right? That the large values that rise up above a threshold are where the hand is actually being generated, and this is exactly what goes on in the ReLU layer. All right, so thresholding, sparsity immediately gives us a ReLU type layer. The third key idea is, if people are familiar with wavelet transforms, is that if we think of going from a coarse scale to a finer scale, what we need to do is, Alex talked about super resolution, right? We need to take this low resolution feature map, blow it up to a higher resolution feature map. It turns out that if you look at the higher resolution feature map, there are micro translations of that feature map when averaged or max pool and subsampled will actually give the exact same coarse scale feature map. So we introduce therefore into the nuisances a micro translation, right? A micro translation in the problem. And again, if you ask what is the optimal inference for a target given a micro translation, it's precisely a max pooling operation that comes out. Okay, so we talked about convolution pops out, ReLU pops out, max pooling pops out. Now, if we think this deep rendering model that we've been speaking about, it's not exactly a tree model, but you can actually prove that for map classification purposes, it behaves just like a tree model, okay, which is a handy point. And then finally, if you look carefully at the computations involved in the EM algorithm for training this graphical model, they look just like a very attractive type of backpropagation learning. It's kind of uncanny. Even some of the tricks like batch normalization, right, that were hard-fought wins by graduate student theses over the years, just pop out naturally in the derivation of the EM algorithm. Okay, a bonus though, for people who are interested in not just supervised learning but unsupervised learning, is because we have a generative model, we can actually use this deep rendering model to solve not just supervised learning problems, but semi-sup and unsupervised learning type problems. So, summary, set up this deep rendering model. We try to solve optimal inference, Cofifi, thresholding, max pooling, and iteration come out naturally. And I invite people to look at the NIPS paper for the full proof. Okay, so how does this approach allow us to bring a bit or answer some of these questions that we posed earlier on in the talk? Well, the first is we can say a little bit more about why is deep learning effective. First, because there's actually a very reasonable generative model that sits behind this inference algorithm. Right? It might not be the best generative model for images, but a multi-scale product of affine transformations seems reasonable, seems wavelet-like, right, or scale space-like. We're exploiting scale in a very natural way. We're doing the right inference, right? We're doing the optimal kind of inference, and we're doing the right kind of training, right? So I would say that really this is the reason, some of the reasons why these methods have been so effective. Of course, we just derived convnets from first principles, and we can also say a little bit more about when these methods fail, right? And of course, when these fail, right, when you have a generative model and your inference fails for a particular problem, then you know it's because your data didn't come from your model, right? There's some kind of model mismatch. So one of the things we're studying now is understanding what the class of images that can be generated by this deep rendering model look like. And something I don't have a lot of time to talk about, but there's some very interesting ideas around how we can extend and improve models or algorithms like convnets, and the nice, and I'll talk just in a minute about just one of those. Okay, so some more implications. Statistical model says that conceivably we should be able to apply the full arsenal of statistical techniques, right, to understand convnets and be able to provide things like confidence intervals, consistency results, the kind of things that are sorely lacking in today's theory of deep learning. Also, we can think of an alternative interpretation or a direct interpretation of this deep rendering model. It's just a very high dimensional hierarchical Gaussian mixture model, right? And so that tells us something, some very interesting things about clustering and other underlying ideas that are going on when you're both fitting convnets to data and when you are performing inference. What is a generative model that when you solve inference under that model gives that set of calculations? This is a non-unique process. There could actually be other generative models out there that are even more natural, more powerful, but their optimal inference still is exactly a convnet. Okay, so that's important. And the next thing that I just want to mention, and there's not a lot of time to talk about it, but this framework is actually really quite general, right? And you can derive not just vanilla convnets from this approach, but also ResNets, which are the current highest performing approaches, dense nets, and even methods that are much further afield. If we replace this process by falling down this tree with a set of affine transformations and replace that with a set of evolutionary changes to the images, then it's actually not very difficult to show that you can generate from the exact same framework methods like random decision forests, which you would think are a completely different set of techniques from convnets, but in fact actually we can now see has actually come from the same family, right? It's a set of that are generated by these tree structure generative models. Okay, so very interesting questions about are there hybrid methods that are somehow share random decision forest like structure, but also convnet type structure. Okay, so in the interest of getting us out of here at 5, let's just summarize. To me, we're still very, very early into the days of figuring out how to best combine physics or models and data. I think that's the thing that I think has been so exciting to me about this meeting, right? Is we're just starting to scratch the surface. I think this deep render model is this one, attempt at trying to bring together these approaches. We're excited about it because of the connections to familiar tools, right? Because There has been rich theory developed for graphical models over the last decades. And the fact that we not only can get nice interpretations of what's going on in these systems, but also principled extensions when standard techniques fail. So there's a lot of interesting open avenues to pursue. Currently, just a few of them, we're looking at towards more realistic rendering models. If you think of generating images by a product of affine transformations, this is not a very very realistic model. And to me, that's one of the really interesting questions is how to make this product of affine transformations more rich. We're interested in application of other kinds of inference problems, new kinds of inference algorithms. So instead of max sum type message passing, other kinds of message passing, unsupervised learning, semi-supervised learning, and also how we can use all the tricks that have been developed over the last decades in EM algorithm learning, facilitate more efficient learning of deep confidence. I will just say one last thing about the application to new kinds of inference problems. We're very interested in applying these kind of techniques to the inference type problems that both Alex and Michael talked about earlier today. In particular, using these deep network type concepts in unrolled optimization algorithms. So taking like lasso type solution algorithms that Alex talked about, and instead of thinking of an algorithm as an iteration of the single block, think of instead unrolling it into a network of multiple blocks, right? These blocks can now be parameterized, as Michael put it nicely earlier today, with parameters. For example, we can maybe have parameters that control the fact that we might not have perfect knowledge of the calibration of our forward model. We can also build in better projections onto the signal space for solving ill-posed inverse problems. And then if we have training data of measurements y and the true signals that generated those measurements, we can train by backpropagation. Alex already talked about compressive sensing problems. This is a compressive sensing problem. These are two state-of-the-art total variation and BM3D based approaches. And this is using this technique that I just talked about in the previous slide. And we see we're not only better in terms of SNR, but about 50 times faster, right? So I think there's a lot of very interesting directions here for the kind of large-scale inverse problems that feature prominently in geophysics applications, for example. Okay, so I will end. We're continuing to plow along in this direction. We're very excited about not just the theory, but also applications for thinking about real neural nets and what graphical models can tell us about real neural nets. But I think it's really important that we have patience, right? Because it is going to take some time before we can really put these kind of neural networks on a firm theoretical model-based perspective.